The next application of derivatives I am going to take up is maxima and minima. First I will give you a brief description of maxima and minima, and then we will proceed with the problems. Now let y is equal to fx be a real valued function with domain df. Then fx is said to have, first is absolute maximum. As the name suggests, absolute maximum is the maximum value of the function in whole of its domain. Absolute means whole of the domain. Absolute maximum is the maximum value of the function in whole of its domain. That is, every other value of fx is less than or equal to this value. This is the maximum value. Therefore, every other value of f is less than or equal to this value. Value of the function at any other point of its domain should be less than equal to the value of the function at a. Then x equal to a is a point of absolute maximum, and the value at this point is the absolute maximum value, and it is the greatest value of the function in whole of its domain. Next is absolute minimum at x equal to a. Absolute minimum will mean minimum value of the function in whole of its domain, and since this value at a is the minimum value, therefore all other values are greater than or equal to this value. This is the minimum, therefore all other values are greater than or equal to this value. Then this value is the absolute minimum, and this is the least value of the function in whole of its domain. We define this as absolute minimum at x equal to a if fx is greater than or equal to fa for all x belonging to df. Next is local maximum. Local maximum at x equal to a. Local maximum, as the name suggests, is the maximum value of the function in its locality. Maximum value of the function in its locality, that is in its neighborhood, that is at the points near x equal to a. This is the maximum value. Local maximum at x equal to a if there exists a neighborhood of a in which this value is the maximum value, that is all other values are less than this value in this neighborhood, then it is the local maximum value. Local maximum at x equal to a if there exists a neighborhood of a such that fx is less than fa for all x belonging to this neighborhood. X not equal to a, because if x is a, then we must have fa equal to fa. Here we have strict inequality, so we exclude this point, and this can be written as there exists an interval containing a, that is interval a minus delta, a plus delta, such that fx is less than fa for all x belonging to this interval. This interval is, if this is the point say a, then this will be a minus delta and a plus delta. Delta may be very, very small. The function has local maximum at x equal to a if there exists an interval a minus delta, a plus delta around a in which fx is less than fa for all x belonging to this interval. For all x in this interval, fx must be less than fa. Fx is not less than fa in the whole of the domain. Fx is less than fa only in this neighborhood. If fx is less than fa in this neighborhood, the condition is satisfied. It will be a local maximum. Absolute maximum is, it should be maximum in whole of the domain, and local maximum is, it should be maximum in a neighborhood of A. It may be a very small neighborhood. If it is maximum in that neighborhood, it will be a local maximum. Local minimum. At x equal to a function has local minimum at x equal to a if there exists a neighborhood of a such that fx is greater than fa for all x belonging to this neighborhood. Fx is greater than fa, that is, this is smaller than all other values. Then it will be minimum. Minimum, therefore it should be smaller than all other values, not throughout the domain. Fa should be less than fx only in this neighborhood. It may not be less than other values throughout the domain, but it should be less than all other values in a neighborhood. There must be some neighborhood in which this is less than all other values. Then it is the local minimum. Fx has local minimum at x equal to a if there exists a neighborhood of a such that fx is greater than fa for all x belonging to this neighborhood, x not equal to a. That is, there exists an interval a minus delta, a plus delta, such that fx is greater than fa, that is, fa is less than all other values in this neighborhood. Now I illustrate these definitions geometrically. Now let this be a graph of any function. What we notice, this value of the function is smaller than all other values in its neighborhood. This value is smaller than these values. Value of the function is known by this coordinate, that is the height of the graph. So this is the minimum value in its neighborhood. So we will say this is the local minimum. This is local minimum. And you can note this value is maximum in its neighborhood. In points near it, the values are less. So this is the local maximum. This is local maximum. And you can note that this value is not the minimum value of the function in a whole of its domain. This value is smaller than this. This is smaller than this. So this is not the minimum value of the function. This is not the absolute minimum. It is minimum only in its neighborhood. And similarly, this is not the maximum value. This value is greater than this. So this is not the absolute maximum. It is maximum only in its neighborhood. Such values are known as local maximum and local minimum. And similarly, you can note this value is minimum in its neighborhood. All other values are greater than this value in its neighborhood. So this value is local minimum. And similarly, this value is local maximum because it is greater than all other values in its neighborhood. So this is the local maximum. And which value is the greatest value in whole of the interval? Whole of the interval, this value is the greatest. There is no other value which is more than this, whose height is greater than this. There is no value which is greater than this. So this is the absolute maximum. This is the absolute maximum. And absolute minimum. Absolute minimum is this. No other value is smaller than this. So this value is local minimum as well as absolute minimum. Absolute minimum. This value is both local minimum and absolute minimum. This value is absolute maximum but not local maximum. Endpoints are not considered for local maximum and local minimum. So this is absolute maximum, but it is not a local maximum. This is absolute minimum as well as a local minimum. This is smaller than all other values in its locality as well as in whole of the domain. So this is the absolute minimum. And what we further notice that here the graph of the function is a falling graph. That is, here the function is monotonically decreasing. As we move ahead, the values are decreasing. Therefore, this is monotonically decreasing. From here to here, it is monotonically decreasing. The graph is falling. And here it is again rising. From this point to this point, it is monotonically increasing. This is monotonically increasing. And from here to here, it is monotonically decreasing. From here it is again rising, so this must be monotonically increasing. And here it must be monotonically decreasing because the graph is falling. Values are decreasing as we increase x. As we move forward, the values of the function are decreasing. And we know for monotonically decreasing functions, f dash x is less than 0. And here f dash x is greater than 0. And here f dash x is less than 0. And here f dash x is greater than 0. And here f dash x is less than 0. So what we notice, for local minimum, function here is monotonically decreasing, and as we cross this point, it becomes monotonically increasing. From monotonically decreasing to monotonically increasing. For local maximum, it must be monotonically increasing to monotonically decreasing. Here, monotonically decreasing to monotonically increasing. Monotonically increasing to monotonically decreasing for local maximum. That is, if we increase x past this point, the derivative changes its sign from negative to positive. As we increase x past this point, the value of the derivative changes from negative to positive. For maximum, positive to negative. Positive to negative. And for minimum, local minimum, negative to positive. Here it is negative and here the derivative is positive. And for local maximum, again this is positive and changing to negative. As we increase x past this point, the value of the derivative changes from positive to negative. This is the first derivative test. Step 1. Solve f dash x equal to 0. Let its roots be, let x be equal to a1, a2, a3. Step 2. If x less than a1 implies f dash x is negative, and for x greater than a1 implies f dash x is greater than 0, then this will imply, this implies x equal to a1 is a point of local minimum. Then x equal to a1 is a point of local minimum. If the sign of the derivative, that is f dash x, changes from negative to positive, then this will be a point of local minimum, and the value of the function at this point will be called local minimum value. You have to check the sign only in points very near to a1. This is the point a1. Let this be a1. And if x less than a2, let this be the point a2. If x less than a2, when x is less than a2, derivative sign of the derivative is positive, is greater than 0. This implies f dash x is greater than 0, and for x greater than a2 implies f dash x is less than 0. If x less than a2 implies f dash x is positive, and when it crosses a2, that is when x is greater than a2, the sign of the derivative becomes negative. That is, the function is monotonically decreasing. Then this will imply x equal to a2 is a point of local maximum. Then this will be a point of local maximum. If as we increase x past a2, the sign of the derivative changes from positive to negative. As we increase x past a2, the sign of the derivative changes from positive to negative. The sign of the derivative changes from positive to negative. And for this, as we increase x past a1, the sign of the derivative changes from negative to positive. Then it will be a point of local minimum. As we increase x past a1, the sign of the derivative changes from negative to positive. That is, the function changes from monotonically decreasing, that is falling to rising. This will be the shape, falling to rising, and therefore this must be the minimum value. If it changes from rising to falling, that is derivative is positive to negative, then shape of the graph will be like this, and this will be the maximum value in its neighborhood. Therefore this will be the local maximum. Note, if f dash x doesn't change its sign as we increase x past a3, then x equal to a3 is a point of inflection. Then it is a point of inflection. Such point is known as point of inflection. That is, the graph changes its trend from concave downwards to concave upwards. Such point is known as point of inflection. Now next is a very important note. If in step 1 f dash x is not defined at some points and those points belong to the domain, f dash x is not defined but fx is defined, that is, it belongs to the domain of the function, then we must also consider these points in step 1. If f dash x is not defined at say alpha, beta and so on, and these points belong to the domain of fx. F dash x is not defined, but fx is defined. Then these points should be included in step 1. Now I come to second derivative test. Here the function must be twice differentiable. Step 1 is solve f dash x is equal to 0. Let its roots be x equal to a1, a2, a3 and so on. Step 2. Now check all these points for local maximum or local minimum. What we do is substitute these points in the second derivative of the function. F double dash a1 is less than 0. This will imply x equal to a1 is a point of local maximum. If second derivative is negative at this point, then x equal to a1 is a point of local maximum. And if f double dash a2 is greater than 0, then this will imply x equal to a2 is a point of local minimum. And if f double dash a2 is equal to 0, then this implies second derivative test fails, and in this case use first derivative test. So if it is easy to find the second derivative of the function, then we will use second derivative test because this is quicker. But if the value of the derivative comes out to be 0, then you will have to go back to the first derivative test. Then you will use first derivative test. Or if the second derivative is more complicated to find, then use first derivative test. Both are easy. If f dash a1 is 0, first derivative is 0 at a1, second derivative is also 0 at this point, we say that the second derivative test fails. There is another method for finding the maximum and minimum. You can find the third derivative. If third derivative is 0, we proceed like this. If third derivative is non-zero, not equal to 0, we will say then a1 is a point of inflection. Then a1 is a point of inflection. And if third derivative is 0, we will find fourth derivative. We will find the fourth derivative. If fourth derivative at a1 is 0, and if fourth derivative at a1 is not equal to 0, then f fourth derivative at a1 is negative will imply x equal to a1 is a point of local maximum. And if f fourth derivative a1 is greater than 0, then this will imply x equal to a1 is a point of local minimum. And if this is 0, we will find the fifth order derivative. f5a1 is 0 and f5a1 is not equal to 0. If it is not equal to 0, or the derivative is not equal to 0, then this will imply a1 is a point of inflection. And if fifth derivative is 0, then we will find the sixth derivative, and so on. So what we do is solve this, and these are the points. Now at x equal to a1, this is 0. Now you find second derivative. If it is negative, then local maximum. If it is positive, then local minimum. If 0, this test fails. In that case, you will find the third derivative. If third derivative is 0, you will find the fourth derivative. If fourth derivative is 0, you will find the fifth derivative till it is non-zero. But if third derivative is not equal to 0, if odd derivative is not equal to 0, then we will say that x equal to a1 is a point of inflection. Odd. If third is non-zero, we will say it is a point of inflection. If fifth derivative is non-zero, we will say it is a point of inflection. And if even derivative is non-zero, we will proceed like this. If f even derivative at a1 is less than 0, then this is a point of local maximum. If f even derivative at a2 is greater than 0, we will say that it is a point of local minimum. For even, this rule will hold. For odd, it will be a point of inflection. If odd order derivative is non-zero, it is a point of inflection. If even order derivative is non-zero, we will check. If it is negative, it is local maximum. If it is positive, it will be a local minimum. The first problem I am going to take up is fx is given to be x cube minus 6x square plus 9x plus 15. And we have to find the points of its local maximum and local minimum, and then find its local maximum values and local minimum values. I will do the questions using both first and second derivative tests, and then we will have an idea in what situation first derivative test is easy and in what situation second derivative test is easy. And then you can decide in each question whether you have to use the first derivative test or the second derivative test. So I will solve all these problems using both first derivative test and second derivative test, so that you can compare both, and then you can decide in what situation you have to use which test. Fx is given to be x cube minus 6x square plus 9x plus 15. F dash x is equal to, now differentiate this. This is 3x square minus 12x plus 9. 3 is common. We have x square minus 4x plus 3. And this can be factorized as x square. Now product of these two is 3. So we have to separate 3 into 2 parts such that the sum is 4. So this is minus 3x minus x plus 3. Sum of minus 3 and minus 1 is minus 4. And product of minus 3 and minus 1 is 3. So this is equal to 3 into x is common, x minus 3. Minus 1 is common, we get x minus 3. So the factors are 3 into x minus 1 into x minus 3. Now put this equal to 0. First step is put f dash x equal to 0, and we get the critical points or the extreme points. So extreme points are x equal to 1 and 3. Now I will use the second derivative test, and then I will do the same question using first derivative test. Now first I will solve this question using second derivative test. Now we find the second derivative. Second derivative will be easy to find from equation 2. Instead of finding the derivative from here, we will find the derivative from here. It will be less time consuming. So this will be 6x minus 12, and differentiation of constant is 0. So this is equal to 6 into x minus 2. So f double dash at 1 is equal to 6 into 1 minus
2, and this is 1 minus 2 is negative, so this is negative. We are not interested in the value. You can find the value, but we are interested only in the sign of f double dash 1. So f double dash 1 is negative. Therefore, x equal to 1 is a point of local maximum. This is a point of local maximum. And now I find f double dash at the other point. Second point is 3. So f double dash 3 is equal to 6 into, say this as 4. From 4 we have f double dash 3 is 6 into 3 minus 2. 3 minus 2 is positive. Positive into positive is positive. So this is positive. Therefore, x equal to 3 is a point of local minimum. If f double dash is positive, then this is a point of local minimum. You can see the side sheet. Now I find the local maximum and local minimum value. Local maximum value at this point is f at 1. So f at 1 is, now substitute in this, we have 1 minus 6 plus 9 plus 15. So this is equal to, now 9 minus 6 is 3. 3 plus 1 is 4. 4 plus 15 is 19. So local maximum value at x equal to 1 is 19. Now we find the local minimum value at this point. So local minimum value at x equal to 3 is f of 3, and this is equal to, substitute here. So 3 3s are 9, 3s are 27. 27 minus 6 into 3 square. Substitute here in 1. 6 into 3 square is 9. So this is 9 plus 9 into 3 is 27 plus 50. So this is 54. So 27 plus 27 is 54, minus 54 is 0, plus 15 is 15. Therefore, local minimum value is 15. Local minimum value at x equal to 3 is 15. Therefore, x equal to 1 is a point of local maximum, and local maximum value at this point is 19. X equal to 3 is a point of local minimum, and local minimum at this point is 15. Now I solve the same question using first derivative test, so that you can compare both and decide which test you have to use in which situation. So first derivative test. Now consider the point x equal to 1. X equal to 1. Now x less than 1. We have to consider the points in the left neighborhood of 1. X less than 1, but we have to consider only points in the neighborhood of 1. Now, this is the point 1, this is the point 3. And since f dash x is a continuous function, therefore it will have the same sign in all points which are less than 1. From 1 to 3, it will have the same sign. And from 3 to infinity, it will have the same sign. So, in x less than 1, in this neighborhood, it will have the same sign as it will have throughout this interval. In right neighborhood of 1, it will have the same sign as in this interval. In left neighborhood of 3, it will have the same sign as from 1 to 3. And in right neighborhood of 3, it will have the same sign as in this interval. So, x less than 1. Now instead of finding the sign for x less than 1, we use a simpler method. We will take any point in this interval because the sign will be same. So take x equal to 0. X less than 1. Less than 1. X equal to 0. So put it here. 0 minus 1 is negative. 0 minus 3 is negative. Negative into negative is positive. So sign of f dash x in this neighborhood is positive. This is positive. And in x greater than 1, You have to write in neighborhood of this. So x greater than 1, it will have the same sign as throughout this interval. So take any point, 2. So at 2, 2 minus 1 is 1, 2 minus 3 is negative. So positive into negative. This will be negative. So f dash x is negative. So what we note is f dash x is changing its sign from positive to negative as we increase x past 1. It is changing its sign from positive. Positive means it is monotonically increasing. That is, it is rising. So it is changing its sign from rising to falling. Monotonically increasing to decreasing. So this will be the shape of the graph. And we will have this point as the maximum. Therefore, x equal to 1 is a point of local maximum. This will be the shape of the graph, and therefore this point will be a point of local maximum. And from second derivative test we had the same conclusion. X equal to 1 is a point of local maximum. Here we also get x equal to 1 is a point of local maximum. And now we consider x equal to 3. X equal to 3. For x less than 3, we find the sign of f dash x. And for x greater than 3, we will again find the sign of f dash x. So x less than 3. Now x less than 3, the sign will be same as for x greater than 1. In this neighborhood, x less than 3, it will have the same sign as for x greater than 1 in this neighborhood. So for x greater than 1, the sign was negative. So here the sign will be negative. For x less than 3, you can take the point 2. 2 minus 1 is positive, 2 minus 3 is negative. Positive into negative is negative. But we know the sign from this discussion. You can use that knowledge. So for x less than 3, f dash x is negative. And for x greater than 3, we can take any one point, say 4. So 4 minus 1 is positive, 4 minus 3 is positive. Positive into positive is positive. So sign will be positive. So what we notice, f dash x is changing its sign from negative to positive as we increase x past 3. Therefore, the graph is f dash x is negative. It is falling to rising. The graph is changing from falling to rising. So this will be the shape of the graph, and it will be a point of local minimum. Therefore, x equal to 3 is a point of local minimum. So x equal to 3 is a point of local minimum. We had the same conclusion from second derivative test. X equal to 3 is a point of local minimum. So you can use either second derivative test or first derivative test. In this question, the second derivative test and first derivative test are taking the same amount of time. The level of difficulty is same. But in the other questions, we will see that in some questions, second derivative test is easier, in some first derivative test is easier or is less time consuming. So you use that test which is less time consuming.